Okay, all right. I think we're recording, so good. Okay, so do you guys have any questions you guys want to go through first? I know there's a few questions on the problem sets that are a little tough to get by at first glance. So if you guys want to take a look at those, just let us know what questions you guys want to do. I don't think, I mean, if no one.
Okay, why don't we get started with the homework set that you gave, and then just go through any questions that anybody had.
Okay, it's on the chat. Okay, Ria's going to be back in a second, no problem. Okay, so do we want to do basic differentiation problems or the definition of limits problems?
Okay, so I know that in my breakout room, some people were confused about the graphing.
The graphing, got it. That's in definition, I think.
Yeah.
Okay. Okay, this one, yeah. These are actually pretty simple. The way you want to think about it is the first thing you want to look at is where does the derivative equal 0? So obviously here the derivative equals 0, and then here the derivative equals 0, right? So where does the slope equal 0? So at these 2 points, the derivative equals 0. So I can actually just plot those here and then here. The next thing you want to look at is where is my slope positive and where is my slope negative? My slope is positive here, right? Here, you guys can see my cursor, right? Okay.
Yeah.
So the slope is positive here, meaning the derivative is going to be positive or x is less than -3. And the derivative is also positive for x is greater than +3, right? So it's positive here because we're increasing here and increasing here. However, here we're actually decreasing. Now, when we're decreasing, if it's like not to infinity, like here, as you can see, the slope goes to essentially goes to infinity, and the slope also goes to infinity here. So essentially, we know that this portion will look like this, and this portion will also look like this. Okay, so these two parts we figured out. Now the middle part, we know that the slope is negative, so our derivative is going to be down here. However, the question now becomes, which point? How do we conceptualize this? Does it look like this, or does it look like this, or does it look? How do we figure that out? The way we do that is we think, okay, where does the concavity change? Do you guys know what concavity is? Feel free to just shout out.
The direction it's facing?
Yeah, exactly. It's the direction it's facing. So right here, up to here, or I can't draw straight lines, as you know. Up to here, we have concavity down, right? Because the function is pointing down, so it's concavity down. And then from here to here, the function is pointing up. It's concavity up. So concave up and concave down. Whenever our concavity shifts, our derivative is going to be at a maxima or a minimum. So here, the concavity shifts. So we're going from 0 slope to more negative, to more negative, to more negative. But then we start increasing, more positive, more positive, more positive, more positive, until we reach 0. That's why this is going to be a local minima, because the slope, it continues to decrease until we reach x equals 0, and then the slope starts increasing again. So if we connect these points, it's a parabola. Does that make sense, the process by which we did this?
Yep.
Oh, cool. Samhitha, do you want to go through some of the other ones?
I actually don't have remote access, but I can just pitch in.
Okay, cool. Sounds good. And then this one right here, you guys know the derivative of a straight line is what? A constant, or I'm sorry, I gave you the answer. But if I have a linear function, what's the derivative?
Straight line. Yeah, straight
constant, line. Straight line, right? Horizontal line. So this is a negative slope, so I know it's going to be somewhere hypothetically down here. Now, I technically shouldn't be putting the arrows because we don't know if this continues on. But you can, I guess you can assume that just because, why wouldn't it continue on, I guess. So what if this function was actually, what if it actually looked like this? Then you would draw a hypothetical just straight line, a horizontal straight line, in the positive, right? Now absolute value, Can someone explain to me how this would work? It's very similar to what we just did, but it's a little bit different here. Does someone want to try?
I guess I could try.
Yeah, go ahead.
So I think since like in the first half of the graph, the slope is negative, you want to like, draw your line in the bottom half of the graph. And then since the second half is, a positive slope, you're going to draw it in the top half.
Exactly. Perfect.
This is an absolute value function, right, MG?
Yeah, exactly. Okay. You're right. And the derivative d dx, and I have a bad habit of saying d over dx, and Ms. Raja corrected that today. It's not really a fraction, it's a differential, right? We talked about this yesterday. It's not really a fraction. We get it from the formula of delta y over delta x, so it comes from a fraction, but it's not really a fraction. So this, if I take the absolute value of x, that is equal to absolute value of x over x. In other words, it'll always be positive 1 or negative 1, the slope, except at what point? When is this function undefined? This function
Zero.
Zero, right? And what do we have at 0? We have a
like a hole, or
hole.
not like
Exactly. The proper term is a. Here, actually, it's not a removable discontinuity. Here, it's a jump discontinuity because we're jumping from here to here. And if you're going to take the AP exam, that's a good term to know. Jump discontinuity, okay? Because we're jumping from here to here. Okay. Can someone try this one? D is a little bit harder. Actually, let's come back to D in just a bit. What about E?
Would the graph like just be on that same line, or would it be like below it? I'm not sure about this one.
For this one, you have to just look at, so for example, for B, we took a linear line and then we took the derivative of that, and then that became just a line like this, horizontal line, right? So here we have a horizontal line. So if you take a derivative of just number, what does that become?
Oh,
yeah.
0. Oh, okay.
Yeah, it's just 0, right? Because, like Samhitha said, this is I could write this, if I wanted to express this, I could say this is y equals c, a constant c, right?
Yeah.
So y prime equals 0. And once again, I'll encourage you guys to participate, because the more you try and think on your own, and the more you, even if you're wrong, it's a learning process, and that's how you'll get better, and that's the only way, in fact, to learn. So it's much more productive if we make this a conversation than just me and Samhitha just saying stuff. Now F, we'll come back to D again, because D is a little bit, it requires more thought. So what about F? This one's an interesting one.
Aren't exponential functions the same? Or at least when you do a derivative?
Yeah. Okay. So if this was e to the x, then it would exactly, the derivative of it is e to the x. So this would just be that. I don't know if you guys know, but f of x, if I were to say f of x equals f prime of x, this is a classic problem. F of x equals f prime of x, tell me what f of x is. The easiest solution to this is e to the x. Okay? All right. Now here's a problem though. Just one small problem. We're not sure whether it's e to the x. So the only one problem is if this were, say, 3 to the x, then its derivative, if y equals 3 to the x is our function, then y prime would be equal to 3 to the x natural log of 3. So it would be 3 to the x times some sort of multiplier. So it might look, let's see, it might look something like this, but it'll still be an exponential function. But for the sake of this problem, just assume it's e to the x, because, why make your life more complicated? All right. Am I good to clear the screen?
MG, can you explain why y prime is equal to 3 to the x natural log 3?
Sure. So that's just one of the derivative formulas you got to remember. It's in the chart. If you remember the chart, so the derivative of e to the x is e to the x, but the derivative of a constant a to the x is e to the x ln, or sorry, not e to the x, I'm so sorry. It's a to the x
natural log
ln a, exactly.
Okay, all right, cool.
Not ln degenerates. There's a lot of mathematicians make jokes about that. So once you get into college, if you ever take calculus in college, you get used to jokes about ln degenerates when you take natural log, whatever. But this actually comes from the chain rule. But you don't need to know the chain rule for the test, so don't worry about that for now. Okay, I'm going to clear this screen. Part D is interesting. So once again, the first step we're going to do is think about where does the derivative equal 0? Anyone, where does the derivative equal 0? Zachary, we're going to say something?
I was just thinking about it. Like, it's because for E, it was 0, right?
At 0? So
Because that's when you have a constant.
right. No, I understand what you're saying, but let's take a look at 0. What's happening at 0 as we approach from the left and from the right? So from the left, what does the slope, what does the tangent line look like? Is that equal to 0, or what does that look like? The slope. The slope is
It
infinity.
gets close to being a vertical line.
It's a vertical line, right? And a vertical line, we say, doesn't have a slope. In other words, we can say it's infinity or negative infinity. So here, on both of these, is this negative infinity or positive infinity? From approaching from the right.
Positive, right? Or,
No, it's negative infinity, right? Let's.
oh,
let's
from the right.
yeah, I can see why you would think that. I thought that at first too. But let's think about this, right? You want to approach. It's all about limits, right? We're approaching from the right. Do you see how these are all negative slopes? And even though, like, that's why limits are important. Because if I didn't tell you that we're approaching from the right, logically, this could be positive infinity. We don't know, right? But because, like, if it was this, that would also be positive infinity. That would also be infinity, but that would be positive infinity because it's a positive slope. But since we're approaching from the right, as you can see, all these slopes are negative. So at x equals 0, from the right, we're going to be approaching negative infinity. So it's going to look something like that. I'm not sure what it's going to look like here yet, so let's not worry about that. Same thing for this side. We're going to be ending here. Now, where does the derivative equal 0? Think real hard here. Where does the slope equal 0 on part D?
Like at the edges, like at the very left and the very
Exactly.
right.
Right? Yeah, the limit, if I were to ask you the limit as x approaches infinity or minus infinity of f of x, that would be equal to 0 because it has a horizontal asymptote of 0, right? Has a horizontal asymptote of 0. So that means our tangent line, if there were a tangent line at negative infinity, it would be 0, meaning this at here, we have an asymptote of 0. Here we have an asymptote of 0 for our derivative. I'm going to switch to a different color for the derivative. So the derivative here is 0. At positive infinity, it's also 0. Here we said it's negative infinity. Here we also said it's negative infinity. Now here are our points of interest. Are these derivatives, are these tangent lines negative or positive? Slope-wise.
Negative.
Yeah, negative. So this is what the derivative from this side would look like. What about here? Is this one negative or positive?
That's also negative.
Yeah, negative. So that's what the derivative would look like. I'm going to let me erase that and then redraw it. So it would be here and here. It might be a little bit over than that. I'm not sure what the answer key says, but conceptually you get the idea, right? And it's not a straight line, it's a curve. But you know, I just can't draw. I can't. So I think you get the idea here, right? Okay, good. And then this one is pretty easy. It's kind of like the same way Gautam let us do the absolute value function. Does someone else want to try part G?
Yeah, why not?
Sure. Go ahead.
So we can see from the left, since the slope is, I guess we can see it as 1, or it's like a positive slope. So we see it's a straight line until it leads to the kind of asymptote. I thought of it as a cusp, so it didn't have a. That's why it's like a hole or jump in this case, actually. And then
yes,
as
in the case, yeah, you're right. In the case of the derivative, it would be a jump. Yeah.
Yeah, it's a different. And then the slope was negative here, so that's why we have the line at the bottom, and we also have 2 other, I guess, holes, or you can say it's a jump.
Yeah.
And then the final line that's going positive has a positive slope, so we start off at the positive side of the coordinate plane, and that's why we have another hole at the end.
So Karan, you're gonna have to remind me, what was this value here? 'Cause I know this is 1/2, right? And this was positive 1. What about here though? What is this? What is the slope here?
I'm not sure what this.
So
this
just
graph
rise
is kinda
over run.
graded.
Let's just calculate it real quick. 1, 2, 3, 4. Oh
Is it
god.
6?
1, 2, 3. 4, 5, 6 over 1, 2, 3. So -2, I believe.
Yeah.
Okay.
Yeah. That's right.
So it would be, that's supposed to be an
Yeah.
open hole, by the way.
Yeah.
Like that? Is that what you guys got?
Yeah. That's what.
Okay, good. Good. All right. Hopefully the graphs make more sense now. All right. Do you guys have any other questions? I know the questions about the tangent lines are confusing. So we can take a look at some of those. But I want to make sure we address you guys' questions first.
MG, could you do the problem right above the graphs? I think there's one about tangent lines. Yeah,
All right.
number 4.
Sure. Number 4. Let's take a screenshot of this and move to Paint. You know, I could actually directly draw on here, but I like Paint better, so we'll use that. Okay. So we're trying to find the equation of the line that is tangent to f of x at x equals cubed. Stop right there. We need to, because whenever we see tangent, parallel, normal line, all these terms, they get really confusing. So just break it up step by step and just think. So we're trying to figure out tangent line of f of x equals x cubed. Whenever we think tangent line, what do we think?
Slope.
Derivative.
Slope, derivative, exactly, derivative, which is slope ultimately, right? So f prime of x is equal to what? Now for this homework, she wanted you to use the limit definition. Do you want to go through the limit definition and then work it out by hand like that, or do you want to? We want to. Okay, Samhitha is saying yes. So let's do that. So the way you would do this, there's 2 ways about going about this. We'll do both. The first is using this definition, the limit as h approaches 0 of what? Can someone tell me the definition?
F of x plus h minus f of x over h.
Yep. And once again, what I tell you is don't memorize this. Think about it conceptually. What are we doing? We're thinking y2 minus y1 over x2 minus x1. y2 is f of x plus h, and then y1 is just f of x, and then x2 is h, and x2 is x plus h, and x1 is just x. So x plus h minus x is just h. Do you guys understand what I'm saying here? Or do you want me to draw it out real quick? Just a diagram of that.
No, that makes sense,
Okay.
MG. I don't speak for everyone, but it made sense for me.
Okay. All right.
Yeah, it made sense. It made sense.
Awesome. All right. So now what I do is, this is really creepy having 2 Samhithas. Okay, that's fine. So now what we're gonna do is directly plug this in. Now we're gonna say x plus h cubed minus x cubed over h. All right. Does anyone know how the expansion of this works? If you guys don't know, we can use Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And the only reason we use Pascal's triangles are for the coefficients. So remember how we have if we have x plus y whole squared, then that would be x squared plus 2xy plus y squared. So these just give us the coefficients. So similarly, for x plus h whole cubed, we would have x cubed plus 3x squared h plus 3xh squared plus h cubed. Do you see how that matches the coefficients? This is called Pascal's triangle, and that's what we use Pascal's triangle for. And then minus x cubed, of course. And then all of that divided by h. So x cubed minus x cubed go away, and we get 3x squared h plus 3xh squared plus h cubed. What would be the best? What would be a good option next? Oh, I've been making a fatal flaw right here. You need to be writing limit as h approaches 0 for each of these. I just don't have space. So when I'm teaching or writing it out on the screen, I don't do that. But when on paper, you need to build a habit of writing limit as h approaches 0 for all of these. Okay? Make sure you just build a habit of doing that. Next step. What would be the next step?
Could you factor out h?
Exactly. And why would we factor out the h current? What's the motive for that?
Well, since h is approaching 0, we don't want 0 to be in the denominator. So if we factor it out, we can cancel from the original
Exactly,
denominator.
exactly. Good. So we're going to factor out an h, and we'll get 3x squared plus 3xh plus h squared over h. H's cancel, and we get 3x squared plus 3xh plus h squared. As h approaches 0, these two terms go away, and we get 3x squared. That's where the derivative comes from. So this is the tangent line, not the tangent line, but this will give us the slope at any point given x. So now that we know what f prime of x is, I'm going to erase all this so I can give myself some more space. I don't think it lets you erase more than that. Okay. So what we'll have to do is do that. Delete that.
Gee, there's an erase tool right there.
Huh?
There's an erase tool in tools. Do you see that?
Yeah, but like you have to, it's really fine and kind of,
Oh, okay, never mind.
it just takes more time. That's fine. And so now that we know that f prime of x is equal to, what did we say? 3x squared, right? And you should know from the power rule that it's 3x squared. We want to find the line parallel. What does parallel mean? Whenever we think parallel, what do we think?
They have the same,
Same
slopes.
slope.
Same slope, right? So we're going to eventually set this equal to the slope of this line. So if I were to set this in slope intercept form, this would be y equals 3x plus 1. What is the slope of this line?
3.
Yeah, 3. So we're going to set 3x squared, our derivative, equal to 3, right? What this tells me is at what point does my slope actually equal 3 on the function? So if I say, go ahead, Samhitha.
I thought you were asking for the answer, but
Oh, go ahead. Yeah, you can explain it.
okay. So then obviously you would cancel out the 2 3's, so divide both sides by the 3's, and then you would square root both sides. But then you always have to remember whenever you square root, you're gonna get 2 numbers rather than 1, so you're gonna get plus or minus 1.
Exactly. So what this tells us is we're going to have a plus 1 and a minus 1. But now what we have to do, now whenever we do tangent lines, what's the formula we like to use? Well, I mean, not formula, but what's this? Remember, there's 3 ways we can represent a straight line. We can either represent it in standard
slope,
form.
maybe?
Yeah, point slope. That's what I was
Yeah.
looking for. Exactly.
Oh, what the?
Because there's 3 ways we can represent a linear function. We can represent it in standard form, ax plus by equals c. We can do y equals mx plus b. Or we can do the third one, which Curran said, which is point slope form. And why do I want to use point slope form? Because that's what we usually deal with. We deal with a point, and we deal with the slope, which is the derivative. So if I do y minus y1 equals m times x minus x1, we're actually going to get 2 equations. Why? Because we have 2 x's for which the derivatives are equal to the slope, right? So the first thing I'm going to do is I'm going to substitute m in. Actually, we'll have to take this step by step. So we're going to have to create 2 equations. So the first is, if my x1 is positive 1, what is my y1 going to equal? So if x equals 1, what is y equal to? Well, all I have to do is plug this back in the original f of x. So if x equals 1, y equals f of 1, which is what? F of 1 is, anyone blurt it out?
Oh, it's 1.
Yeah, 1, exactly. So what we're going to do now is we're going to say y minus 1 equals m times x minus x1, and x1 is just positive 1. So what is our slope here? Our slope, as we said, was just 3, right? M equals 3. So we're going to set that equal to 3. So y minus 1 equals 3 times x minus 1. I should say 3 times the quantity x minus 1. And then if you simplify this, this is y equals 3x minus 3 plus 1 is minus 2. So that should be one of your equations. The other equation would be, we would have to take x equals negative 1 now. And what would y be? Y is equal to f of negative 1. And what is f of negative 1?
Negative 1.
Negative 1. Good. So y plus 1 equals 3 times x plus 1. So this would be y equals 3x plus 3 minus 1 is plus 2, right? And this should make sense. If these are our two answers, if I think about x cubed, it looks something like this. At x equals 1, we have, okay, once again, I can't draw properly, so you have to understand that this is a challenge for me. But essentially, we'll have a tangent line here. We'll have a tangent line here. We'll have a tangent line here. And the original line, y equals 3x plus 1, would be somewhere here. Once again, I can't draw. So just think about it conceptually, right? I have my function. I have a tangent line here. I have a tangent line here. And then the original function that I was looking for is here. And they're all parallel to each other. Why? Because their slopes are equal to each other. Does this make sense how you do these problems? You always want to start with the derivative, then relate it to the slope of the line that's given, and then put it into point slope form. Okay? All right. Any other questions?
Krishna asked, do you think we're going to be able to graph derivatives of the trig functions?
Have to graph. Okay, so when you're graphing derivatives of the trig functions, it's really, really easy. All right. All you got to think is, I'm going to clear everything over here. All you got to think is if I have y equals sine of x, actually, I'm just going to pull an image off the internet because it's much easier. So sine of x, because I can't draw it properly. So we're just going to use this. Actually, why don't we just use Desmos? So if we use Desmos and we just graph sine of x, right? And we want to graph its derivative. What's the derivative of the sine of x?
Cos of x.
Cos of x, right? So we'll oh, I'm using red and red. I should be. Let's do orange this time. So I'll have cos of x just starts here, has a minute or goes to 0 here, has a minimum here at -1, 0. Oh, I made that too far. That should be here, and so on and so forth. So I think you get the point. Obviously, I'm not going to draw it properly, but graphing derivatives of, yeah, it's pretty easy. And then obviously, if you have cos of x, its derivative is what?
Negative sine of x?
Negative sine of x. So this will be -1. Or sorry, not -1. This will be 0. Then we'll go down to -1. Then back to 0. Then to +1. Then back to 0. And so on and so forth. And then we can do this. And so on and so forth. So this is the graph of minus sine x. You see that? Does that make sense, Krishna? You shouldn't have to be able to graph the derivative of tan of x, but we know that this is tan of x, and the derivative of tan of x is sec squared x. And that's what this looks like. So if you're ever unsure, just go ahead and graph it in your calculator, and then get a conceptual understanding of it, and then go ahead. Because what's happening here? Once again, if we really wanted to do it without our calculator, think about it. When is the concavity? Remember how I was mentioning concavity? As you can see, it's just repetition. So really what we need to be able to do, if we're going to try and graph the derivative of tan of x, is just focus on one of these lines. We don't need to figure it out for every line, because once we do it for one line, it just repeats over and over, right? So what happens to the slope as we approach negative infinity and positive, not negative infinity and positive infinity, but like the edges? What happens at the edges? What does the slope equal?
Oh, it becomes 0, doesn't it?
No. What's happening here? Is that 0 or what?
Vertical. Undefined.
Undefined. It's positive.
Undefined. Oh my god, yeah, I accidentally switched it.
No, it's okay. It's okay. So that this is how you learn, right? So we see that we're gonna get positive infinity here, and we'll get positive infinity here. Now the other question is, where does the concavity change? Where are we changing from concave down to concave up? Where are we doing that? Can anyone see that point where we're changing concavity?
After 0, or after y becomes 0, or after like y becomes like positive, like that's when the concavity changes, kind of?
Yes, at x equals 0 is when concavity changes, right? So as you can see, up to here, we're facing down, and as soon as we get to x equals 0, we're concave up. So what do we know about when the concavity changes? That means we're going to have a relative maxima or a relative minima in the derivative. So here, obviously, no, in the ends, we're reaching positive infinity. So that means you can't get higher than positive infinity. That means this here, at x equals 0, we must have a minima. And the minima isn't actually 0. The slope here seems to be 1. So it'll probably be around here, right? And as we get, so from positive infinity, as you can see, the growth slowly gets less and less positive. It's still positive, but it's getting less and less positive. And here, it's getting more and more positive. So that's why we're getting less and less positive. And then we're going to get more and more positive, right? And that's how you get the graph of secant squared of x. And then obviously you'll repeat that. So let's see how close we were. X squared of x. And do you see how it looks like kind of like a parabola? Repeated parabola?
Yeah.
That's how you do this. That's exactly what we were doing with the graphing problems. It's the same idea. You just look at the significant points and then you try and sketch a graph. Okay? I think we have about 5 minutes left, so we'll try and wrap up. Do you guys have any other questions? I know we covered a lot yesterday, so hopefully that helped. But do you guys have any other questions from here? Or even the other packet?
Yeah, for the other packet.
The other packet? Sure. Let's take a look at it. This one?
Yeah, can we go over like one problem of either the product or quotient with the trig?
Okay, product, quotient, or trig. So with
Yeah,
trig, so this
right
one?
there, one of those.
One of those,
Yeah.
like on number 3 or just in general?
Can you go over 3D or 3G? One of them.
Let's do, we'll start with 3D. Let's do that. Okay. Sticking tool again, new. Okay, and if this meeting ends and if we're not finished, just rejoin using the same link. All right, guys? We'll try to end, and if you need to leave, yeah, we're not going to hold you or anything, but okay.
Wait, sorry. Just before he starts this problem, if you guys do have any questions between like tonight and tomorrow afternoon, there'll be a little like question thing up on our Instagram, and we can answer any questions on there too.
And feel free to put it on the Slack as well. Either way works. And the better thing is try to answer each other's questions, because the more you do that, the better understanding you'll have of it as well. So let's start with this. So we'll have f prime of x. Okay, so what do we remember about doing this? It's low d high minus high d low over low low. So we're going to take low, which is sine x, plus 1. D high, what's the derivative of the numerator? The derivative of the numerator is 1 plus sec squared x, right? So low d high minus high, which is x plus tan x. D low, the derivative of the denominator is cos x, or just cos x, because plus 1 becomes a 0. And the denominator, what do we have?
I think it's a denominator squared.
Yes, so v. Hi, Alina. We're about to end this meeting. We'll rejoin using the same link. So
Okay.
yeah. So sine x plus 1 whole squared, right? So does it just ask you to find the general derivative, or does it ask it for a specific point? So just in general. So honestly, you can leave I think for AP, you could actually just leave your answer like this, because this is a lot. But if you wanted to simplify it, we have a minute 45 left here, so we can do this real quick. To simplify, let's just do this real quick. Sine x times 1 is sine x. Then sine x plus sec squared x. So sec squared x is 1 over cos squared of x. So if I think of this as 1 over cos x times 1 over cos x, and I'm multiplying this by sine x, I'll have a tan x, right? Sine x plus tan x, and then that'll still be sec x, tan x, sec x, plus 1 plus sec squared x minus x cos x minus tan x cos x, but tan x is sine over cos, so cos and cos cancel, and this becomes sine x. I know I did this real quickly in my head. You guys understand how I did that? Because tan x is sine over cos, so I should write sine x over cos x, and because we're multiplying it by cos x, the cos x's cancel, and we get sine x, and that's all over sine squared x plus 2 sine x plus 1. Okay, and I'm not going to do any further because that's complicated enough. All right, and that meeting's just about to end, so just rejoin with the same exact link. All right, I'm going to actually just end it because I don't want to start something else and then get me interrupted. All right.